In this video, we describe transformations on functions. There's 6 transformations of functions I'll name. Let's begin with vertical shift. A vertical shift means that if you're given a function, say y equal f of x, then the up or down shifting of this function, say k units, transforms the function to this. If the function is shifted up k units, then we have a plus k added to the function. If the function is shifted down k units, the function form transforms to this. So suppose we had this original function here, and suppose this function is, say, y equal x squared. If that function is shifted up, for example, say 1 unit, the function's form would change to y equal x squared plus 1. Next, let's look at horizontal shifting. Suppose again you have some original function, say y equal f of x. If this function is shifted to the right h units, the function's form will change to y equal f of x minus h. And if the function is shifted to the left h units, the function's form will change to y equal f of x plus h. So suppose we had original function, say y equal x squared, and you shift this function, say 3 units to the right. The new form of the function would be y equal x minus 3 squared. All right, let's move now to the next transformation. This is a vertical compression or stretch. And if you have some function, say y equal f of x, the transformed function is y equal afx. So you can see that we're multiplying the original function by a factor of a. If that a is between 0 and 1, then there's a vertical compression. If a is greater than 1, then there's a vertical stretch. So for example, suppose we have this original function, y equal f of x. If a is 2, for example, this dotted curve here shows that the original function was stretched vertically. So that means it's increasing faster and it's decreasing faster. All right, and if a is between 0 and 1, then it's a compression, a vertical compression, right, given by y equal 1/2 f of x, for example. So to transform a function y equal f of x to y equal afx, all we're doing is multiplying all of the y coordinates of the original function by a. All right, moving on to the next type of transformation. We got here a horizontal compression or stretching. Again, if you're given an original function, say y equal f of x, then that function transforms to y equal f of ax. And if a is between 0 and 1, there's a horizontal stretching. If a is greater than 1, we have a horizontal compression. So you can see here that for the original function, this solid curve here, if a was, say, 2, then you can see that this was compressed horizontally. We compressed this function so that it appears steeper. It appears to increase more rapidly and decrease more rapidly. And the same goes if A is between 0 and 1, then there's a stretch horizontally. So it's similar to the vertical compress or stretch, but almost the opposite. And to transform a given function to y equal f(ax), all we're doing is dividing all of the x coordinates of the original function by a. All right, let's now look at the next transformation. Is called the reflection about the x-axis. Suppose you have some curve, y equal f of x, and you reflect this about the x-axis. So in other words, I'm rotating the x-axis 180 degrees so that this curve now appears to be this curve. And you can see that the effect of that is that all of the y coordinates are multiplied by negative. So to transform y equal f of x to y equal negative f of x, all we're doing is multiplying all y coordinates of the original function by negative. All right. Next, moving on to the last transformation. This is a reflection about the y-axis. So you got some original function, and then to reflect that function about the y-axis, we're just rotating the y-axis 180 degrees. And so to transform an original function, say y equal f of x, to y equal f of negative x, all we're doing is replacing x. Everywhere we see x in the original function, we're going to replace those x's by negative x. All right. Now, in order to better understand transformation of functions, it would be helpful to know by memory some common key functions and their graphs. For example, these are some common key functions that anyone should know by memory. And there's probably some more, and I just listed some of them here. So for example, y equal x squared. We need to know the graph, what this graph looks like, and it's this graph here. So from this graph, you need to know the function, and that is this, and vice versa. If you're given this function, you need to have in your memory that this graph looks like this. And then we got the y equal x. This is just a diagonal line through the origin going up. I didn't bother to draw this graph. And then we got y equal absolute value x. That is this graph. And we got y equals square root x. That is this graph. Y equal 1 over x. This is called a reciprocal function. I did not bother to draw this graph. And y equals cube root x. I didn't graph this one either. Y equal x cubed is this graph. So we need to know the function and its graph. And if we're given a graph, we need to know by memory what the function is. All right, if we do know that, it'll really help in understanding transformations of functions. Now let's look at some examples. These are typical questions related to transformations of functions. Suppose you're given this graph below. What function best describes this graph? Well, we can see from earlier, without knowing the common key functions and their graphs, we're going to be lost. But if we know that, the characteristics of the key graphs, like this graph is a V-shaped. So anytime you see a V-shaped graph, you may quickly think that it's an absolute value function, right? So this graph, some kind of way, this graph here is an absolute value function. And we can see the transformations that took place here. So first of all, y equal absolute value of x has the graph, is a graph like this. Right? So we can see that this graph, from this graph, let me make a little arrows on the end. This graph here, to get to this graph, we had to move 2 units to the left. Now, by moving a graph 2 units to the left, or shifting 2 units to the left, the graph would become y equal absolute value x plus 2. Right? So that would make us have, the picture for this graph then would be something like this. Y is x, and maybe like this. And here is -2. All right? And then you can see that from that transformation, we reflected about the x-axis. So when we reflect about the x-axis, we're going to have y equal -x, absolute value x plus 2. Right? So the final function here is the graph of this. Here's the transform function for this graph. All right, so this is one type of question that's common related to transformations of functions, to recognize, if given a graph, what is the form of the function that matches this graph. All right, let's look at another question. Suppose here we're given a function and they're asking us to write the transform function if it was transformed this way. What would the new function look like? So here's the original function, y equal x cubed. And we want to know if this function is shifted down 4 units, for example, what is its new function going to turn into? So you can see that when you're shifting down, up or down, the function y equal f of x becomes y equal f of x plus or minus k. So in our case, we're going down 4 units. So our function is going to become then y equal x cubed minus 4 is our final answer for that transformation. All right, let's look at number 2. This time we're shifting to the right 2 units. So you know from earlier that whenever you're shifting to the right or left, the original function, say y equal f of x, transforms to y equal f x plus or minus h. Now we go plus if it's shifted to the left. we go x minus h if it's shifted to the right. In our case, we're shifting to the right 2 units. So our transform function is going to become y equal x minus 2 cubed. All right, let's move to the next. This time we got a reflection about the y-axis. Now for a reflection about the y-axis, if you have an original function, say y equal f of x, any transformation that is a reflection about the y-axis takes an original function and transforms it to y equal f negative x. Right, so everywhere we see x, we're replacing it by negative x. All right, so we had our original function, which was y equal x cubed. So that new function is going to become y equal negative x all cubed. And when you simplify this, you're going to get y equal, negative x cubed, like that. So I'm multiplying, I'm doing negative x times another negative x. And the outcome, the final result will be negative x cubed. All right, and then next, here we're doing a vertical stretch by a factor of 5. So anytime you got a vertical stretch, you're taking an original function, say y equal, let me just circle this. You take an original function, say y equal f of x, and you're transforming that to y equal a f of x. So in our case, all we're doing is multiplying by 5, the original function by 5. So we're going to have our final answer for this one is going to be y equal 5x cubed. Right, so this is like multiplying all y coordinates by 5. All right, moving on to the next. What is a horizontal stretch by a factor of 5? Well, for a horizontal stretch, we take an original function, say y equal f of x, and when we do a horizontal stretch, the form of the function changes and becomes y equal f ax. So in other words, we're replacing all of the x's by a of ax. And this is, it means also that we are taking the x coordinates of the original function and dividing each of those x coordinates by a factor of a. So our transform function is going to become y equal 1/5 x. And we're taking this and we're taking it to the third power, right? So this is going to become, and now when I raise this to the third power, this is going to become x cubed 125. Because 5 times 5 times 5 is 125. All right, so here are the answers to those problems. Now let's move on to the next type of question that's commonly given related to transforming functions. In this case, we're asked to find the function that is finally graphed after the given transformations are applied to the function y equal square root x, and perform it in a certain order. In other words, after shifting up 2 units, what would this function look like? What would its transformation be? So again, like we said before, anytime you're shifting up or down, a function is just added by that number of units. So here we're going to have, this is going to become y equal square root x plus 2 as our final answer here. And then next, when you take this same function right here that we had and now reflect it about the x-axis, it means you're going to multiply that function by negative, right? So all I'm doing now is I'm multiplying it by a negative. So I'm taking whatever that function was, and it was square root x plus 2, and I'm multiplying it by a negative. And when I multiply it by a negative, I still have to distribute that negative so that it becomes negative square root x negative 2. So here is our final, here is our next transformation, right? After we started with this one at first, this was our original equation. And then when we shift up 2 units, this is how that equation changed. It became this, and now we take this function and now reflect that function about the x-axis, and it then becomes this form. All right, now we got one more transformation to do here. We want to now reflect this function about the y-axis. And reflecting a function about the y-axis means replacing each x-coordinate by negative x. So everywhere I see x, then I'm going to change it to a negative x. So negative square root negative x, and everything else stays the same. All right, so here's our finally transformed function. After all of these transformations in order, this one, next this, and finally this. This is our final function after all of these transformations were performed. All right, let's do one more problem related to this. So again, here we're starting from square root x, like we had before here, y equals square root x. And now we want to perform these transformations in order. So we can go a reflection about the x-axis like before. We just, multiply the y coordinates by negative. So this is going to become y equal negative square root x, right? And then next, shift right 2 units. So next we're going to have, when we shift right 2 units, we're going to have x minus 2, that. All right, next, take this function now and shift down 3 units. So our final answer is going to be, shifting down 3 units, we're going to have here minus 3. Right, so here is our final function after all of these 3 transformations are performed. All right, I hope you all understood these and are getting a better understanding of these transformations. It really does take a lot of practice to get this. It's really not an easy subject or concept to grasp. All right, let's look at another example. This time we're given a graph of a function. Say this graph is y equal fx, And we want to use this graph to come up with this transformed graph, this transformation. We want to perform this transformation on this graph, right? So just looking at the form of the transformation that we are supposed to take on this function, we can see that the form is we're adding 1 here. So just looking at just this part of the function, this is telling us we have to shift the original function to the left 1 unit. And then if we look at this part of the transform function, it's telling us we have to shift the original function down 2 units. So we got 2 transformations happening. Shift to the left 1 unit, and then shift down 2 units. So all of the x coordinates are going to be shifted to the left 1 unit, and all of the y coordinates decrease by 2. All right. So we can go ahead. The best way to do this is to go ahead and list all of the coordinates for the original function, which are here. So here are the coordinates for the original function, right? And then after we perform the transformation, in other words, a shift to the left 1 unit, it takes all of the x coordinates and moves them to the left 1 unit. So negative pi then becomes negative pi minus 1. Negative pi over 2 becomes negative pi over 2 minus 1. 0 becomes 0 minus 1, and so on. And all of the y coordinates are shifted down 2 units. So 0 becomes negative 2, negative 1 becomes negative 3, and so on. Right? So after we go ahead and graph that function and plot the coordinates for the new function, the graph looks like this now. So you can see that it was shifted to the left 1 unit, and then it was shifted down 2 units. Right? This point right here used to be right at the origin, but now you can see that it's moved over 1 unit and it's shifted down 2 units. The increments here on the x-axis are pi over 4. All right, so I hope you've seen how we did that. All right, and then the next function, we wanted to transform that same function, perform this transformation on this function, right? So this means we take all of the x coordinates and divide them by 2, right? Because this is a horizontal stretch or compression, right? So all of the x coordinates, I'm going to divide by 2. So you can see what the original x coordinates were. They were negative pi over 2, and so on. So again, I'm going to set up the tables for both the original function and the transform function. And you could see here, let's see. So here's a table, and all of the x coordinates I'm dividing by 2. So negative pi over 2 divided by 2 becomes negative pi over 4. Pi over 2 divided by 2 becomes pi over 4, and so on. So once we have all of the coordinates here for the transform function, we just plot those coordinates. And here is the final graph, and you can see that it is compressed horizontally. Right? Now its domain is negative pi over 2 to pi over 2 when its original domain was, its original domain was see here, negative pi to pi. So it's got squeezed or compressed, I should say, horizontally, right? I hope you found this video to be helpful. This was the math of numbers and symbols, but we feel that math is order in the broadest sense. Together, let's end disorder. Also, check out our cool shirts at the website in the description below.